In this video, we're going to take our spring example and convert it into a MATLAB process. What we're going to do is start by building our objective function. And going back to this calculation here, we're going to base it off a vector of x values and y values, which are the x and y coordinates of the nodes in our problem. So I'll start a new function. It returns the energy level, and let's call it spring energy based on x and y. And we'll add a comment that x is a 5-element vector, and they're both 5-element vectors, so we'll say that. And then our challenge is to build our vectors like v1, 2, and that's going to be a vector built in the x coordinates from the second x minus the first x. This is our n minus start idea. And same thing for the y values. And what we can do is repeat that 5 times. And we can change that to 2, 3, 3, 4, 4, 5, and 5, 1. Change this to 3, and yes, we would hope for a better way to do this. For people in the truss problem, you should be thinking about that kind of logic, but for now, for an example that's not going to get repeated, this is as good as any method to get us started. But we should do a sanity check at the end of that process. Good. v1, 2 goes from 2 to 1, v2, 3 goes from 3 to 2, and v3, 4, 4 to 3, 4 to 3. This looks all good so far. We then calculate the energy for each of those. E1, 2 is going to be 0.5 times k, but k is 1, times the length of the vector currently. So this is the length of our spring distance. The actual length here, actual length, is equal to the norm, or the double bar line here, of v1, 2. We can take that in MATLAB as norm of v1, 2, and it's how far that is away from the natural length of the spring, which is 2. And we're going to square that. And we are going to do that 4 more times, or 5 times in total as well. And same thing, 2, 3, 3, 4, 4, 5, 5, 1. And now we can simplify this, 2, 3, 3, 4, 4, 5, and 5, 1. And we'll save that as spring energy while we're here. And then our energy is simply the sum of those ingredients. And that, in principle, is our entire calculation for the potential energy of the spring. Actually, of all 5 springs together. Any configuration of x and y values, we have the lengths there. Oh, we didn't account for the lengths changing. The length 2 only applies to the first vector, the first spring, and then it's 3, 4, 5, and 7. So we need to capture that. That's in these calculations here, 2, 3, 4, 5, and 7. Now we have the correct energy calculations for the 5 springs altogether. So notice what we did here is we said x was going to equal a vector of x1 to x5, and y was equal to y1 to y5. There is no particular reason we needed to do that. Are there other options possible? Absolutely. We could have called it P1, P2, P3, P4, and P5, and had them each be x, y values. Totally up to you. I usually figure the fewer inputs, the better. If we can package more things in it and use fewer labels, that's usually safer, but there's no right answer to how you represent those 10 numbers, those 10 coordinates. Next up, we want to write a main script that'll use fmin search to find a minimum energy configuration of those nodes. So this is where we do the search, and these files tend to be remarkably small. So this is W103, and the main thing we need to do is create a starting value. Let's actually start with our search though. So at the end of the day, we want to search for an optimal V value and an optimal F value. Actually, it's called E, opt, because it's our energy. And that's going to be an fmin search of some vector-based function with some starting value and some options. We'll even leave off the options for now. We'll just leave it as is. And the challenge then is to define our function which has a single input. So remember, our function that goes into this program, into fmin search, can only have one input. Ours, of course, has, going to the top, 2 inputs, x and y. So we have to accommodate that transition. And this is something that's best done on paper. And there's two ways that sort of make the most sense, I think. Noting that we have x1 through x5 and y1 through y5. And the v doesn't actually have to be a vector if we don't want it to. V can actually be a matrix. So one of the nice ways to keep things organized is to simply make our v be all the x values in the first row and all the y values in the second row. Or if you like, first column, second column. We're going to use this format as one choice out of many possible choices. So what does that mean? V is a 2 by 5 matrix. X in the first row, y is in the second. And that means when we get a vector in, if someone hands us one of these matrices here, then what we want to do is take the first row out. Well, the first row is the first row with all the columns, and that is going to be our x value. So we're going to call spring energy with the first row of v as x. Well, that's exactly what the first input to this function should be, comma, the y values. Well, the y values are on the second column of v. Second row, all the columns. And that would do our search for us. Someone gives us a v value. This line breaks it into the first row and the second row, which we interpret as, going to our function, the x values and the y values for the 5 nodes. So we are on our way. The only other thing we actually really need is v naught. And we could build it one way, but I think it makes more sense to start with x naughts. And heck, let's start with the layout here. Let's start this with x equals 0, 2, and 5, say, 0, 2, 5, 4, and 1. So that's our x values. 0, 2, 5, 4, and 1. 0, 2, 5, 4, and 1. Our y naught, our initial starting values for y. Do those as, say, 0, 1, 2, minus 2, minus 2. Again, the whole point of the optimizer is it's supposed to take those starting values and do something smart with them afterwards. So 0, 1, 2, negative 2, negative 2. That should give us roughly the configuration you see on the screen here. And then the optimizer should shift those values until we get to a lower energy configuration. Well, we don't have x naught and y naught though in our search. What we have is v naught. Well, we're going to do the opposite of what we did here. We're going to build v naught as x naught in the first row and then y naught in the second row, and that'll build a matrix of the form we want. It'll be these guys and these guys, and we can actually check that. Never hurts to check. Copy paste. When we look at v naught, it is in fact those 5 x coordinates in a row, and then this next row down, the 5 y coordinates. So this is one way to translate the concept. So here, conceptually, we usually think of the nodes as being a list of x and y values. Okay, how do we strong arm, shoehorn in our vision for this as an optimization tool when the optimization tool can only have a function that takes in one argument only? We have to really think about how we're going to package, and that's all it is. How do we package all of our inputs, all of our 5x values and 5y values into a single thing? Well, here we call it v, and it's 5 elements in the first row, 5 elements in the second that are our x and y coordinates. And so a lot of thinking going on there, but literally we are ready to run this and see what happens. All right, we hit a little error. Let's scroll up and see what we can find. A nice simple typo. Best kind of error ever. Norm, 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 and norm. And the v's go inside those. That's what the typo was. There we are. What we're going to do is put a little CLC at the top of this so we get a fresh start every time in terms of clearing the output window. And, oh, I think it ran. Oh, it did run. The values we get back are not the values we started with. So somehow the X and Y locations have been tweaked. This is the point where you think, gosh, it would be nice if I had some options set. So let's use optim set to turn on the display, because that just kind of happened and I didn't really know what was going on. So let's add the options at the end of that. What that should change is now it'll search and give us some output as we're going. Let's give ourselves a little bit of room in the output. Ah, lovely. Notice this is taking quite a lot longer than our earlier search, but we do see 500 iterations, 400 iterations. Here's the actual energy level. So the energy in all the springs is really quite low by here, and it gets down to really essentially zero. For the last few steps, we're kind of wasting our time because we're not getting much improvement, but it's working. We have turned this problem of having 5 locations tied together by springs of different lengths, and trying to minimize the energy in it. We should be able to achieve energy 0 by having these at their natural lengths, just kind of laid out in some kind of pattern. And it looks like fmin search is doing that for us. This is very exciting. Now, it would really be helpful if we could actually see what's happening though. This all feels like it's going very well, but we don't know for sure. And even the plot at the end, or the output at the end, we have some X and Y coordinates, but we don't really know whether it's right. Maybe we get some sense because this points at 2, -6, and this is close to 0, 0. Maybe those are 7 apart from each other, which is what we want. But it would be really, really nice to see that in action. And this is where we would typically overload our spring function. We've calculated our values, now add some plotting. So what we could do here is plot the X values and the Y values. There's 5 elements in each. We're going to plot those as, let's say, black dots. Make them decent size. Let's say 20. And let's just see what that does for a second. We might need the draw now. Let's put that in now just as a default. Otherwise, we don't necessarily get a refresh on the screen. And in fact, it's hard to tell what's going on. It's certainly taking longer. So let's stop that for a second. Control C is your friend for this. We're also going to put a close all on here, so any new windows pop up in front. Oh, that's what we're looking for. What we're seeing are these points moving around, though it's flickering on the range here, so we maybe could fix that a little bit. Let's go and add an extra ingredient, which is xlim and ylim. Let's go from -1 to 6, say, and ylim from -1 to 6.2, just to see what happens. If we run that now, nope, we're missing some of the values down low. All right, we'll fix that. But we can see the configuration happening here as it tries to get these lengths working out to the correct length. Control C again, and we'll just expand our viewpoint here. Let's go -6 to 6, -6 to 6. There's, again, other ways you could do this. Right now we're settling for something that gets us some quick feedback about what's happening. Ah, lovely. So you can see it trying, and there's another one down here. That's where the other one is. In fact, it'd be really nice if we added the lines, because it's hard to tell which ones are actually connected here. And this is where you get the natural refinement of, this is almost what I want, but not quite. So let's add the springs, which only connect some of the lines. So we would have plot x1 to 2 and y1 to 2. So we grab the x first and second element, y first and second elements, and draw those with a black line is fine. And then we repeat that 5 more times, or 4 more times, 5 in total. And then it's 2 to 3, 3 to 4, 4 to 5, and then it's just 1 and 5. So notice it's not a colon for this last one. I just want to join x1 and x5. 2 to 3, 3 to 4, 4 to 5, and 1, 5. Go back to our main script, run it. Little error in our calculations here somewhere. Unexpected bracket. Right, we need to round off, or we don't need those square brackets, because the vector's being built in those commands, and we run it one more time. Oh, lovely, except the 5-1 isn't working quite the way we expected, and we are getting a lot of grass going on here. So we'll stop that for a second. Go back to here, and because we have the hold on and we keep plotting and plotting and plotting, we really want to have a clear screen each time. So we're going to clear this and look at this 1-5, which isn't quite working the way we expected. And right, it'd be better to do it this way. Because we don't have a natural pairing, let's say x1 tied to x5 in square brackets. And likewise for this one, let's make a vector the old-fashioned way, y1 to y5, close the bracket. That'll be the way that'll actually connect those two that aren't adjacent to each other. Ah, there we go. So we're searching, we're searching, we're searching, and we can see the values dropping here. And interestingly, it doesn't seem to form into a circle for whatever reason. It's totally fine. All we asked is that the lengths be correct. And after a while, we start getting pretty close to a configuration that makes sense. But we also notice that fmin search is taking more steps than it maybe needs to. I don't really care about this level of refinement. And so we're going to talk about that in a later video. But there's a way to set an option so we only do a certain number of searches and then we return the value. Because the problem is with Control-C right now, I've lost any of the answers that I found. If you stop fmin search before it's done, it throws away all of the work that is done so far. But for now, quite frankly, this is awesome. This is doing exactly what we had hoped it would do, which is searching for a layout, a configuration of these nodes. It's moving 10 variables at once, and it's doing the heavy lifting for us. We do not have to intervene. It's finding a minimum energy configuration. We are good to go.